Welcome back to our first Q&A session of ViViMaT. This time, we interviewed Tomas Babuska and Krishnanand Shukla, coming right up after this message. Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis. And as Carsten already mentioned solid lubrication, I don't know, do you want to ask Tomas something?
Yes, definitely. I liked all the presentations, but as I said, as I'm right now figuring out some proposal for the German Science Foundation, I was, of course, very much interested in this particular presentation. So, Thomas, I was wondering a bit because I had a chat with a friend of mine from KIT in Germany, and he said, okay, there are some new views on how solid lubricants mainly work. And I still have this kind of old picture in my head, you know, this deck of cards mechanism, how things slide over each other. And when I was looking into the literature, well, I could not find actually that they propose some kind of a new mechanism or a new picture. Is this still valid actually in the community for most of the solid lubricants as the mechanism at all? Or is there something new that I just missed when reading literature? So I'm talking about the deck of cards mechanism.
Yeah, so I think the deck of cards mechanism is actually still more of a theory because no one has really shown where the sliding interface is in these solid lubricants. We know that you get a transfer film, of course, so that you have a self-mated contact or MOS2 on MOS2. We also know that sliding can induce some sort of recrystallization or reorientation of your coating, typically to get some sort of basal orientation or surface parallel crystallites. Now, how that process evolves is still kind of unknown. And I think the only other model I know of is it's called soft interface fracture, I think. I think there is one paper on that, but there are not a lot of publications looking at or kind of understanding how solid lubricants work. I think a lot of it's just kind of some hypotheses, and there's not much out there.
Yeah,
honestly.
I was getting desperate. I said, did I miss something important, or what the hell is going on? Because you usually, you're screening literature and then people tell you, that is old stuff, forget about this. It is old-fashioned, and then I got a bit, okay. Or maybe a good opportunity to ask Thomas in the presentation or in our Q&A session today if he knows about something particularly new. Thomas, another question regarding molybdenum disulfide, because I know that also regarding temperature and humidity, or maybe to start with the temperature, how much does molybdenum disulfide actually tolerate in terms of temperature increase before it starts to give up? Because you find in literature also many conflicting numbers. Can you shed some more light on the reality and on the truth? What is really going on?
Yeah, so that's actually kind of funny because we are actually in the process of drafting another paper on temperature-dependent friction of MOS2, and actually some of our interesting findings were a hint there actually is no temperature dependence of MOS2 if you do it in a ultra-high vacuum environment with a very pristine coating. Kind of there's like a lot of boxes you have to check. So there are a lot of conflicting papers out there. I think the point at which a coating can withstand the temperature depends on the environment. Obviously, if it's in like a dry nitrogen environment, so less oxidating or less oxidative, then it could withstand a higher temperature than, let's say, if it's in like a humid air, because it'll potentially oxidize. Now, the friction doesn't always increase significantly. I think as you go hotter, you might see a small increase, but what's gonna typically happen is you'll probably find a drop off in the wear rate, and you'll get premature failure of the coating. But I think MOS2 doesn't actually start disintegrating or breaking up until really hot temperatures of like 500 C or hotter.
Okay. So even But if you assume, for example, oxidative environment, would you then still say, okay, until 500 or 350, or is that basically hard to say, even under oxidative environmental conditions?
Yeah, that I would say, from my experience, it actually depends upon coating to coating variation. MOS2 coating, solid lubricants is a field where you can get the same coating from 5 manufacturers and they are completely different, even though they claim they're the same. We actually get we get the manufacturer to make the 5 of the exact same recipe, and the coatings can perform, one can be 100 times better than the other for almost no apparent reason. But the temperature, I would say probably 250 is where we oxidize our coatings. I have taken them up to like 400, and as you get up to about 400, they start to turn white, which is basically moly trioxide. So I'd probably say like around 350, 400 is probably where you're going to see some real degradation, and the coating starts to turn amorphous, and it gets really, really porous, kind of gets etched away.
Okay, great. Yeah, perfect. So this is somehow, good to know, because there are a lot of papers ongoing, and sometimes it's hard to find precise values or intervals, or if you find something that's really much conflicting.
If you're still, let's say, willing, I have, I don't know, let's start with Tomas maybe. So when I listen to your talk, I mean, I don't know much. I'm not an expert on MOS2, definitely not. But you did such a good job of explaining it that it got me to thinking. So I'm wondering how well understood and known that mechanism actually is, by which those, let's say, grains or flakes of randomly oriented MOS2, how those rotate, and do I have to imagine that more like a sort of a spreading of peanut butter on toast, and that it also fills the cracks, or is it more like a sort of a roof tiling, or do we not know?
Yeah, that's a good question. The challenging part is when you to look at the sliding surface. We do cross-sectional TEM most of the time, right? But you're kind of looking perpendicular to how the sliding is, right? So the problem there is you can really only see this if you're looking at it. You can kind of see the stacking of crystallites, and it's really hard to tell if they're kind of like you said, like a roof tiling. Are they hatched, or what's going on? Because it's challenging. Ideally, you would do a top-down TEM where you'd kind of pull it out and look at it. That's kind of challenging. I don't think we fully understand how that sliding surface looks, and that's kind of one of the. It's challenging to look at. Ideally, you'd look at it in situ or something, but there's challenges with that. So, I don't know if it's like a smearing effect. In some coatings, you do get, due to sliding, the wear scar becomes smoother. So I think in some of those cases, you can imagine it like a smearing of peanut butter, where you're kind of smoothing out the surface. But yeah, we don't quite understand it. There's the initial starting morphology of the coating could probably affect how that happens. I do think so. The in-plane strength of MOS2 sheets is quite strong, so you can see sometimes, or you can imagine it if you have this vertically oriented coating. So if you can imagine if these crystallites are oriented perpendicular to the surface, that sliding kind of bends them over. So they kind of pulls them and bends them over flat. But if you get some sort of hatching, I think the mental model you can think of is that you probably do get some sort of like a roof, kind of, where there's one over another. I think that is a good mental model, but we don't really understand it kind of at this moment.
But so the way I understand it, you think it's rather unlikely that two flakes would then really bind and close that gap somehow. that's
No,
less likely.
I don't think that's necessarily less likely. I think you actually do, depending on the sliding parameters, I think you actually would get some recombination of these flakes or crystallites to where they would become larger than their initial starting size. We have kind of started to try to probe that mechanism using Kelvin probe force microscopy, looking at surface potentials, because there's a lot in the literature where the surface potential can change based on the size of a MOS2 flake or crystallite, because you're basically measuring the amount of defects, where a defect is essentially just an edge site where you have basically some molybdenum where there's no bond terminated. So you can imagine the surface potential would increase with an increase in this flake size. I think our colleagues at Sandia just published a paper in Tribology Letters looking at that quite recently. I'm not sure if it's online yet, but I think it might be. But yeah, there's just a lot unknown, which is kind of impressive for this material being like 80 years old.
Yeah. Well, thank you very much. Those were good questions for really hand-waving, good answers to hand-waving questions.
Yeah.
Thanks a lot, though.
Coming to your presentation, Krishnanand, which I also enjoyed very much, as you reported on these cobalt, chromium, and molybdenum alloys. So I have a couple of questions also here. First of all, you showed that you have this kind of, in your morphology setup, a hardness gradient layer that you showed of one of the initial slides. Can you explain again actually why you need that kind of hardness layer gradient? Is this for as an adhesive promoter, or what is that for, or to compensate any kind of tangents in the coating, or what's the purpose of that?
So basically, in high PIMS coating, usually the adhesion is not the issue, because we follow there is a special way of etching the surface. But when you using any metal like a biomedical alloy like titanium or cobalt or some steel, right? There are some condition of cyclic and static loading, right? And in that case, no matter how strong adhesion is, it will break at some point. And to avoid such damage, because once you are, it's inside the body, it's painful, expensive, and it's a rigorous process, frankly. So the idea is that usually, nothing is new in it, but the idea is how we can implement this all technique together. So make sure that you have a hardness or stress gradient. Best way to describe stress gradient, because substrate is very soft. It's in case of Vickers, you can go 450 HV. In case of nano hardness, it can be 7 to 8 GPa, but based on which kind of alloy is that. So, and then in top of it, when you do alloying like nitriding, carburizing, oxidizing, so you basically, what we trying to achieve is that to develop a layer which varies the hardness, okay? And on top of it, then you can deposit some adhesive layer like chrome nitride, titanium nitride, niobium, or zirconium, whatever, and then super lattice coating like 2-3 nanometer of each layers. Mm-hmm. Once you have this kind of structure, it assures that there will be a less chance of damage in case of fatigue condition, like when you imagine you have a knee or hip, so every time you are running, jogging, do all kind of heavy stuff, right? In this situation, this is very important to have such kind of structure. One of our work, we have described this behavior. It's easily available on Science Product and ResearchGate. And it's very interesting to see that what is the effect of the stress gradient on impact fatigue as well as static loading condition. Yeah.
Mm-hmm. Okay, thank you very much. And then I saw, I think it was on figure 2, when you showed for your alloy system the 0.5 kilometers, there were 2 plateaus actually. Can you please summarize again what
Can
is
you again?
happening? It's on figure
Can,
2. Figure
yes.
2, and there is, I think it's the upper left figure for the 0.5 kilometers.
Okay. Yes.
There are 2 plateaus visible. What is assigned
Yes.
actually again to the 2
So
respective plateaus?
yeah. So basically, what idea was, because cobalt chromium has some of these metals which are highly reactive when you expose to the air, or maybe even in the biological environment, that they react quickly. Best example is chromium. Chromium reacts quickly, whether it's air or it's in the simulated body fluid. It makes oxide quickly. So we wanted to understand first what is happening when it's a dry. So because the tribal layer formation, in our case, what we have found that it's based on not just, even if you fix your load, it's based on your sliding distance. So in starting 0.5 kilometer, we found that it was just removing. If you literally observe the track, there is nothing, no oxide, no via debris, because everything is coming out from the side, right? But as soon as you increase this distance, you start seeing the islands, right? And these islands basically nothing but is a chromium or molybdenum oxide. There is no cobalt. Hardly we see cobalt, but they are not adhered to the track, right? And further, if you increase, what is happening? That these islands are becoming a big, thick layer of oxide layers. It means, imagine you have a depth of 12 micron. Now it decreased to 10 micron. Means it's depositing now because of reactions. So that's what we observe here. In that, if you see the friction coefficient friction plot, you can see that this is just removing the material. And then after 1.5 kilometer, before 0.5 kilometer, you can see there is a stable region that defines that there is no more room to remove things. It just now, it start reacting with oxygen available in the environment. I think that was the answer you were looking for.
Yeah, perfect. Are you guys actually doing also developments in HiPIMS in your department, or are you just using the technique to deposit the coating?
No. So my group is a main one of the major group which work on HiPIMS. We were the it's so much debate, but we are the one who develop lots of coating using HiPIMS as well as the HiPIM technology. So commercializing of HiPIMS was from here.
Okay, that's very good. Then I have a pretty good question to you, because I'm interested in it. What are the recent trends or recent developments actually then in HiPIMS? Is there anything groundbreaking coming up soon, or is there what is the current ongoing development in that sector?
It's very interesting. Frankly, I cannot define. I cannot give you idea in 1 or 2 minutes. But I can invite you to join our conference, which is next week. Yes, and it's very interesting because slowly the industries are picking up the HiPIMS. It's a bit expensive, but the property which it promises, it's amazing. You can do coatings of some of the material which is not possible with RF or other technique. So you will. It's very interesting. You can join us for the, and I think it's going to be online. So yeah.
Yeah, excellent.
So we do. Yeah. So this conference basically we do together with Fraunhofer IST Braunschweig. Yeah. So it would be interesting if you join.
Let's stay in touch then. Yeah.
Yeah.
Well, thank you very much. Yeah, that's for the moment. I think you have to leave anyway in a couple of minutes. So
yeah, no, it's just the rule in university is that either one of the staff member has to be here.
Okay.
And once a staff member is gone, you have to leave. Yeah. That's it.
No problem.
Yeah. Anyway, thank you very much, everyone.
Yeah.
Take care. Bye.
Well, thank you for joining.
Thank you for joining.
Yeah.
It was great.
Yeah.
Bye bye.